So sorry about that, guys. My Wi-Fi cut out, and so I want to pick it up right where I left. So we'll have two videos for today's class. Um, Fishbone creation, again, the main categories you could use. You don't have to use P4M&E. You can use something specific. I'll give you an example of cooking a proper hamburger. And below each major category, you define subcategories, and then enter each cause category in a box. Connect the box to the spine, and the measurements category groups root causes related to the measurement and measuring of a process activity or output. So examples of questions to ask: is there a metric issue? Is there a valid measurement system? Just to give you an idea of what goes in each of the P4M&Es. The manpower one: are people trained? Do they have the right skills? Is there person-to-person variation? Are people overworked? And the methods category groups root causes related to how the work's done. How is it performed? Are procedures correct? What might be unusual? And materials: are bills of material current? Are parts or supplies obsolete? Are there defects in the materials? And you kind of just ask those kind of questions for each of the subheadings in order to build the fishbone. The environment, Mother Nature: is the workplace safe and comfortable? Is the company culture aiding or hindering the process? Are outside regulations impacting it? And you put them all together, and each of the small spines for each area goes on the fishbone. And then you start looking at, all right, can we get the root cause here? What are one or two things that are likely causing the what? And you analyze the diagram as a group. Use a Pareto chart to filter causes. Remember Pareto we did back a few weeks ago. Identify cause with high impact and agree to them, because the gaining agreement's the biggest part of it, just like A3, and then determine how to measure. And the benefits are: helps us identify and sort potential causes, provides a systematic way to brainstorm, and identifies areas requiring data collection for further quantitative analysis, and locates low-hanging fruit. And the limitations are: it only provides quantitative analysis of correlation between each cause and effect. One cause and effect diagram can only focus on one effect or event at a time. And then we need to do some further statistical analysis sometimes to quantify the relationship between what we identify on the fishbone. And here's an example of one. And this one here, I did use P4, actually, P4M&E. It's basically about why bad burgers. I think I stole this from Wall Street Mojo. You see machines. We're looking at storage and cooking equipment, whether it's maintained properly, it's cleaned properly, that kind of thing. I'm looking at methods. Is the recipe right? Is it flawed? Are people following it? And then the materials might be raw material. We buying cheap burgers. Is it filled with fillers? How about the packaging? And then environment: is it too hot? Humidity. Measurements: incorrect quantity. We're not measuring our spices close enough. We don't have a way of doing that. And then mishandling. So as we went through a correlation, we're just going to cover correlation today, and we'll get linear regression next week. And again, this is a very, very fast review because we kind of went through it with the age and the salary. And again, the homework for those that joined late is to go ahead and do the correlation Pearson's R, 3 different ways using my pulse and weight data. The correlation is a statistical technique to describe how strongly 2 or more variables are related. We looked at age, the age of a person, and their salary. Is there a correlation between that with 10 pieces of data? And the analysis helps to understand direction and degree of association. Of the different metrics to measure correlation, Pearson's R is the most popular. And again, I want to reiterate, this is probably my favorite tool. I really enjoy. I have fun with this one. It's also called Pearson's correlation, is called Pearson's R, or coefficient of correlation. And R is a statistic measuring the linear relationship between 2 variables. So the correlation coefficient will range from -1 to 1. If it's a 0, there's no linear relationship between the variables. If it's a 1, that means there's a strong positive correlation between variables. So what we saw with the age and weight, the age and salary, is a strong positive correlation. In other words, as people age, they tend to make more money. And the homework would be to find out if there's a strong correlation between my weight and pulse, or pulse and weight. And the sign means the direction of the relationship. So as we explained when we went through the exercise, that if I had gotten a Pearson's R of -1, that would tell me that there's a strong negative correlation between my age and salary, people's age and salary. So in other words, as they age, they get older, their salary goes down. And when the correlation is strong, the data points on a scatter plot will be close together. We did a scatter diagram. We saw that we had a strong positive correlation, not a cloud like this. When we do a scatter diagram and we got like the Milky Way here at 0, it means that there's no relationship at all between salary and age, or my weight and pulse, whatever. So the closer the correlation is to 0, the weaker the relationship. And as we saw in the example, we were very close to 1 for the age and salary. Correlation does not imply causation. So if variable A is highly correlated with variable B, it doesn't mean that A causes B, or vice versa. It's possible that an unknown third variable is causing A and B to change. For example, if an ice cream sales at the beach are highly correlated with the number of shark attacks, it doesn't imply that increased ice cream sales causes increased shark attacks. They're triggered by a third factor, which is summer. And the correlation coefficient could be high or low by chance. It may have been calculated based on too small samples that do not provide good inference on the correlation between two populations. And that's why it's always good to go do a normality test, just to make sure that our process is stable and in control. So if we test whether there's a statistically significant relationship between two variables, we need to run a hypothesis test to determine whether the correlation coefficient is statistically different from 0, so the normality. And we could use the function Correl, which I showed you guys, equals Correl, highlight my data, and that's part of the homework. A scatter plot, again, we did that very quickly, 6 seconds. And again, this is redundant. Perfect positive is a 1, moderately positive 0.4 to 0.8, none, no correlation at all. Then we'd have a moderate negative, -4 to -8, and then a perfect negative. And the limitations are, it helps us to spot interesting features in the data. It doesn't provide quantitative conclusions. So we might have to do some further statistical analysis to assess whether the association is statistically significant. We might want to measure the strength of the relationship between variables, determine whether outliers, which we're going to cover next week when we get into regression in the data, and then quantitatively describe the pattern of the data. This is a positive linear correlation. And this is a weak positive linear correlation. And this is 0. This is none. No correlation between two sets, X and Y. And we have outliers. You may have outliers. We didn't see any today. You may see it in my weight data. Well, you guys can tell me. We're going to talk about how we handle that next week. And then we get into regression. Again, I apologize for this Wi-Fi of mine. I'm going to definitely get away from cable and go to fiber optic. Have a great afternoon. I'll send you all the math practice and recordings.